Let's hammer down some of our jargon and terminology that we're going to be using when we talk about solubility. Now, if something is strongly attracted to water, it might be able to dissolve. And if it can, we're going to say that it's soluble. So that would be an example like this atom here, or molecule, or whatever I happen to have sketched, popping loose because this water molecule has dragged it away. The stickiness that this molecule has to the water is big enough to overcome the stickiness it has to its neighbors. And so it's actually going to gain in stability when it does that. Now, if it's more strongly attracted to its neighbor than it was to the water is going to stick to it maybe, but it's not going to pop loose. An example of that might be something like glass, where we have those ions in the glass crystal lattice, but they're so tightly attached to their neighbors that the water sticks to it but can't pull loose any of those atoms. As a result, the water does kind of stay on the surface pretty easily and pretty tightly, but it never does manage to pop this loose. Now, in that case, this solid is going to be called insoluble. Now, a few of those are going to dissolve. Not very many, but a few. Limestone would be a good example of that. We know that limestone is a rock and it's insoluble. However, we also know that a tiny amount of limestone dissolves. That's why when water evaporates off of it in a cave, you get those stalactites and stalagmites. Well, that's something that I really want to point out. We're going to call things insoluble if they don't dissolve very much. Boy, that sounds really arbitrary and vague, doesn't it? You bet. So what we're going to do in later chapters in this text and any chemistry course is we're going to stop talking about them with such hard and fast rules and such a finite kind of terminology as soluble and insoluble. And instead we're going to start talking about these as being in equilibrium. Whether they're dissolved or sticking as a solid is going to be an equilibrium process. If you remove all of the dissolved ion, more is going to dissolve. If you put extra ions around, some of them are going to stick. That's the idea of equilibrium. And it'll be something we come up with later on. And we're going to be able to answer solubility in a much more mathematical way later in the semester. Now, I also want to remind you that heat energy is all about vibration. It's about how much the individual atoms are vibrating against each other. And if you have enough kinetic energy, occasionally one's going to pop off all by itself. Well, what about the idea of having the water molecules also hot? What's going to happen is those water molecules will be able to occasionally dissolve something with more ease. And so more of these can get dissolved and stay dissolved at high temperatures. And that's something you've probably seen before. That's why if you've got hard water, all that calcium ion has dissolved into your water when you're taking the shower. But as soon as the water cools back down, what happens? It deposits that lime scale behind, leaving that white powdery residue on some of your tile and your sink and things like that. We can also get more salt to dissolve in hot water than we can in cold water because the hot water molecules, it's almost like if you're picturing them as being these giant radioactive ants on crack. They're holding on and they're grabbing as much as they can, like some sort of a B horror movie from the 60s. And they manage to pop it loose. Well, if these atoms are holding on really tightly and those ants are trying to pull them apart, one ant can't do it. Maybe two or three working together can. And if they can't, maybe they can if they get a running start to yank it really hard. That's exactly what we're talking about when we say that it's hot. When it's hot, it has more thermal energy, more energy of motion, and it can yank them apart with that sudden jerk and manage to pop them loose. Solubility increases at high temperatures and decreases at cold temperatures because of that change in kinetic energy.